Good evening, class. My name is Reinout Landegem, and my partner's name is Pikaso Dutta, and we are going to be giving the weekly update for March 28th on our project, which is titled SPY and Sector ETFs Pattern Recognition through K-Means Clustering and Technical Indicators. Our academic advisor is Dr. Kashana. So for our project, we are going to be studying the volatility as well as the normalized price graphs for the 9 sector ETFs that compose the S&P 500 index. On the right is an image that shows the 9 different ETFs that compose the SPY. We want to identify patterns in the volatility and normalized price graphs using two methods. The first method we will be using is a time series clustering method, and the second method will utilize artificial neural networks, which Pikaso will talk about. The main question that we are trying to answer for our project is, which of the 9 sector ETFs delegates the SPY volatility and price movements the most? This will allow us to forecast the SPY more accurately while reducing the overall risk when investing. So the first main method we used, as I mentioned before, is the time series clustering method using R. We used a time series clustering package called DTW-clust. It compares different stocks, or ETFs in this case, and groups them together into a given amount of groups that you set it to. After downloading the data off Bloomberg and converting the data into a proper format, we use this tool to do just that. The image you see on this slide is dividing the 10 ETFs into 3 different clusters based on historical price data movement of the ETF. From the image, we can pretty much conclude that XLF, which is the financial sector ETF, has a price movement that is very, very different from the other ETFs, which is something that we expected. We can also see that the SPY is most similar to XLK, which is the tech sector, and XLE, which is the energy sector. For next week, we will be experimenting some more with the number of clusters, as well as adding and deleting more ETFs to potentially generate some new clusters to study. Additionally, this past week, we have also started writing the report, and for next week, we really want to get a big chunk of that done, so we can start focusing on the coding and analysis in more detail again.
Now let us discuss on our second part of the project, which is with neural network. So last week we have prepared our input data with technical indicators, where we have considered VIX as our dependent variable and ADX as the independent one. So in data preparation on our test train data, we'll be working with 26961 data points, which we had split in 80-20 ratio. Now we have taken 60 time steps for one output, which means we are training 1 hour of 1 minute data to predict the output, which will be 61st minute, and this will continue on a rolling basis. Now for the RNN setup, we used stacked LSTM with the optimizer as ADAM, and for calculating the loss, we used mean squared error and set the epoch to 30. So the graph below shows our test results, which we have taken just from 60 data points from a subset of 5,000 test data set. And the model took more than 2 hours to get trained, and finally we found that the train loss converts to only 3.6, and the train and test accuracy is below 50%. So from this data we can conclude that the model is not yet good for prediction. So now you see that ADX might not be a good predictor, and hence we are also going to test this model with other predictors or by creating a composite indicator to find the best combination to predict the VIX and accordingly to increase the training accuracy and the test accuracy.